This is an equilibrium of a rigid body problem with a distributed load going across the top. I like to solve this using a three-step method. The first one is to calculate the distributed load and figure out the distance that load is from the origin point. And in this problem, the origin point is point A over here. And then after that, I like to draw a free body diagram. You already have one drawn here. Just to save some time, we'll go over that in a few minutes. And then from that free body diagram, I like to determine what unknowns we have and solve for those unknowns using our summation equations. So let's go ahead and get started on that. When it comes to a distributed load, the first thing I like to do is just kind of take a look at what we have to see like what unique shapes, because we have to find the specific area to determine the actual locations that these loads apply on the beam. So as you can see here, we have a rectangle that opens up to a triangular shape. Obviously we can't really find the area of that, so what I like to do is try to break it down into multiple shapes. In this case, you can extend the rectangle further to make one long rectangle, and then there will be a triangle above it. So let's go ahead and do that real quick. So as you see now, we have this rectangle that's going to span the entire length of the beam, and then above that we have a triangle. So we'll go ahead and break these down to, we'll call that shape 1, and we'll call this shape 2. Now the next thing for us to do is we need to find the areas for these shapes. So starting with shape 1. Now finding the area is pretty standard. It's in this case it'll be the length times the height. What we use for the height is the pound per foot rating, which is our distributed load. And for the rectangle, you can see that it goes up to this 50 pound per foot rating, and then it stays the same all the way across. And then we have a measurement length of 21 feet. So for the area, we'll go ahead and multiply 21 times 50, and then get an actual individual force rating from that. So we'll go ahead and do 21 times 50, and that gives us a value of 1,050 pounds. Now for shape 2, we have a traditional triangle. So an area of a triangle, we'll go ahead and use the area of a triangle formula, which is 1/2 base times the height. And then as you can see here, the base of the triangle is 9 feet. So for the height, it can get a little tricky because sometimes you can get confused and use this 100 pound per foot value here. But just remember that the triangle starts at this midway point where this 50 pound per foot rating is at. So you just have to subtract this from the 100 pound, which turns out to be 50 pounds. So we'll go ahead and multiply the base, which is 9 feet, by the height, which is 50 pounds. And that gives us a rating of 225 pounds. Now for the distance, for a rectangle, all you have to do is just find the midway point that this distributed load goes across. So since it goes across the entire span of the beam, you just only have to divide the length by 2. So for shape 1, that gives us a length of 10.5 feet. And now for the triangle, triangle's a little different. The way I like to do it is whenever a triangle is opening up left to right, so you have the tail end to the left and it's opening up to the right, considering that you use these axes here where x is positive in the right direction, I like to multiply the base by 2/3. So we have a base of 9 feet, and then we're going to multiply that by 2/3. Now if the triangle is going left to right, like the opening is starting from the left and then closing towards the right in the positive direction, you're going to go ahead and multiply that length by 1/3. Now since we're left to right in our problem, we're going to go ahead and use this. So 9 times 2/3 is equal to 6 feet. Now this 6 feet begins at the 12-foot mark here. So the length from the origin, you have to make sure that you add this 12 feet. So that'll just be 12 plus 6. And that's equal to 18 feet. So after you kind of get these forces determined and what distances they should be, you can go ahead and draw your free body diagram, which is what we have over here. As you can see, our force 1 is here at 1,050 pounds, and it's at a distance of 10.5 feet from the origin. And then we have 225 pounds for our second force, which was the triangle, and it's 7.5 feet from the first force. And the reason why that's a little tricky is because remember that this original length was 12 feet, but this length was 10.5 feet. So you have that difference of 1.5 feet plus the 6 feet that you calculated here for the triangle. So that's a distance of 7.5 feet between the two forces. And then over here is just a remainder 3 feet to get you the total. And now for the supports. They're all designated already. You can reference your book to tell you like what each support does when it's supporting an object. So for example, this roller support here only applies one force onto the beam in the Y direction. So that's what we have drawn here. Now, a pin mount will always exert two forces, one in the Y direction and then one in the X direction. So now looking at this free body diagram, you can see that we have 3 unknowns. So obviously we can't solve all of these at the same time using summation of forces in the X and Y direction. So we know that we're going to have to take a moment of a point to eliminate some of these variables. So it'd make the most sense to eliminate AX and AY. So we're going to go ahead and eliminate or take a moment around point A so we can solve for point B. So we'll go ahead and get started on that. When it comes to finding a moment around a point, I always like to designate what direction I predict that moment will rotate around, and then the general practice is that it will always rotate counterclockwise. So I'll go ahead and draw a positive sign going into the counterclockwise rotation, and then we're going to go ahead and get the summation of moment around point A. And then just to recap, moments are calculated by multiplying the force times the distance. So, and then now that we predicted that this is going to be spinning in the counterclockwise direction, we have to actually look at our free body diagram and determine what each force is doing to it. So if you look at this 1,050 pounds, it's pushing straight down, which would cause this beam to rotate in the clockwise direction. And then if you look at BY, which is pushing up on the beam, that's going to cause it to rotate the counterclockwise direction. So anytime that it's opposite from what we predicted up here, that means it's going to be a negative value. So when we're calculating the moments of these forces, they're both going to be negative values. So we'll go ahead and start writing down what we need to multiply. First force, and that was at a distance of 10.5 feet. And then the 225 pound force is also going to be in the negative direction since it's pushing down on the beam. So we're going to go ahead and put a negative sign here. And that's going to be multiplied by 18 feet because we have the 7.5 plus 10.5, and I'll give you 18. And then the last part of this is our unknown variable. which is a by, or the force of B in the y direction, and this spans the entire length of the beam. So you're just going to go ahead and multiply that by 21 feet, and that's going to be a positive value. So go ahead, plus by times 21, and that's equal to 0. So after you multiply all these out and isolate the variable on one side, you'll get by times 21 is equal to 1, 4, 3, 7, 3, 7.5. Then divide each side by 21, and then you'll get a force value, by is equal to 718 pounds in the positive direction. Now that we have by solved for, we can go ahead and use our summation of forces equations for the x and y direction to solve for ax and ay. As you can see, ax is the only one going in the x direction, so that's pretty straightforward. I like to, when I do my summation of x and y forces, I like to show which direction is positive. So we have the summation of forces in the x direction, and that's going to be equal to this ax over here, and there's nothing else there. It's a positive ax, and that's just equal to 0. So ax is equal to 0. Now for the y direction, since I'm using just a regular positive y-axis, we use the same directions for all our forces. So you have ay pointing up here, and that's going in the positive direction, and then our two forces here are pushing down, so those both could be negative values, while by is also pushing up, so that's going to be a positive value. So go ahead and write all these out. So you have ay minus 1050 minus 225 plus 718, and that's going to be equal to 0. And then that gives you a value, ay is equal to 557 pounds in the positive direction. So that's it. The big thing is just in the beginning, just try and figure out the best way to break up these shapes. A lot of times you might get weird shapes, and just try and figure out how to separate it where you can get the areas cleanly, and then how you can determine the distance, especially for triangles, because they can be tricky. And then just draw a clean free body diagram like what we have here, and then it just really lays out the unknowns. And then once you have a kind of a clean diagram, you can determine it's easier to determine what plan of action you want to take. So like this is pretty much a giveaway that we need to find the moment around point A, and then we can just solve for all the variables from there.